Hello everyone, and welcome to this discussion on absorption and reflection of radiation. Now, when radiation hits a surface, it can either be reflected, absorbed, or transmitted. For this unit, we're going to neglect transmission. So the transmission part is going to be 0. And what we're going to do then is use the reflectivity and absorptivity to determine how much radiation gets reflected and absorbed. Now, like emissivity, these things are going to depend on wavelength, angle, and temperature, and so on. And the preferential absorption and reflection of this kind of radiation is actually responsible for our perception of color. For something to emit light in the visible range requires temperatures higher than 1,000 Kelvin. We know the environment around us is not 1,000 Kelvin. So our perception of what color something has is due to reflected light. So for instance, a red object is going to absorb the blue, green, and yellow parts of the light, but it's going to reflect the red parts. And then the cone cells in your eye that detect red are going to preferentially absorb red wavelengths, and that's going to cause some electrochemical change in the cell that your brain interprets as red. Now, rod cells in the eye can detect ultraviolet radiation. However, the human lens absorbs the UV, so we don't see it. Some people, though, who have had their lenses removed or they've had artificial lenses put in, report actually being able to see UV light. We cannot, however, see infrared radiation, so we don't see the vast majority of thermal radiation. We're not able to see it. So to get a little bit more specific, the absorptivity here measures the percentage of the radiation coming in that gets absorbed. It depends on the spectral distribution and so on, temperature, the nature of the surface, and so on. However, as with emissivity, we're generally going to use the average value, like we see here. The reflectivity also measures the percentage of radiation incoming, but it measures the percentage of that incoming radiation that gets reflected back from the surface. It's bidirectional here. The reflectivity depends on both the incoming direction and the leaving direction. However, as with emissivity and absorptivity, we usually work with average values. And if we look at the average values for an opaque object, the total radiation incoming has to equal the absorbed plus the reflected. So that means that the absorptivity plus the reflectivity has to equal 1, and we can use that reflectivity is equal to 1 minus absorptivity. The reflection from the surface can be either diffuse or specular. Diffuse, if it's a dull surface, it reflects the radiation equally in all directions. Or specular, if you have a shiny surface like a mirror where it's perfectly reflected. And then we can actually determine the net radiation heat flux in terms of our emission and our absorption. So we have emission is how much radiation is leaving, and absorption is how much radiation is coming back. It's important to look here at the behavior of absorptivity and reflectivity to understand really what's going on. I want to make a couple of points here. If you look at snow, so if we take a look at the spectral reflectivity for snow, we can see it's very reflective in the visible light range from about 0.4 to 0.6 micrometer wavelengths. However, if we look at infrared, where most of the thermal radiation is, it's a very good absorber. So snow would look black in infrared because it wouldn't reflect very much light. It's also important to take a look at the white paint line here. We can see that white paint is a good reflector in the visible range. However, it's a very good absorber in the infrared range. So painting something white, like painting your house white, is actually going to have very little effect on the heat coming into your house, or for instance your air conditioning bill during the summer, because it's not going to change the amount of infrared radiation being absorbed very much. So it's not going to have that much of an effect. So we have to be careful about things like that. The next thing we're going to do is just talk very briefly about Kirchhoff's law. It's a way we can actually simplify our radiation heat flux calculations even further. We have to make a couple of assumptions. Either the irradiation or the surface has to be diffuse. And if we have to have either black body irradiation or a gray surface. Now, I want to note here that if we have diffuse irradiation from a black body, this is our cavity. So an object inside a cavity automatically satisfies Kirchhoff's law. However, there are some other conditions. If you have an object that's not in a cavity, then we need to have this surface be gray, and we need to define what a gray surface is. So for a gray surface, the absorptivity and the emissivity don't depend on wavelength. And this doesn't have to be everywhere. It only has to be for the wavelengths that are important for the problem. So in this diagram, we can see the incoming radiation is in this range. And if we go up here to the emissivity is pretty much flat in this range. It's very close to flat. And then the emission is in this range, and again, the emissivity is very flat. So in this case, the substance is gray and would satisfy Kirchhoff's law. However, if we look at a similar problem, but we say the irradiation is over here, and we go up here, we no longer have that constant emissivity. It's decreasing depending on the wavelength here. So in this case, this material would not be able to be considered gray. Even though it's the same material, we've changed the conditions of our radiation interaction, and now we can no longer make that assumption. So if we can assume Kirchhoff's law, we can actually derive the Kirchhoff's law, which is that absorptivity is equal to emissivity. As I said, this is also valid for cavities. Any substance in a cavity. So we can redefine or rewrite the net radiation heat flux like this, by removing the absorptivity from the radiation and putting it over, replacing it with the emissivity. Now, if you have a cavity with black body irradiation, you can further modify this to replace G with the Stefan-Boltzmann law for the surroundings, so sigma T surroundings to the fourth. And you get the radiation exchange from the large surroundings that act like a cavity to the object that we're looking at.